Okay, so this is for Chapter 14, Inputs and Outputs for the Fanuc Handling Tool, or MAT 150. So in this chapter, we're going to talk about, how you use I/O signals, different types of hardware, how to configure them, how to monitor and control them, set up and apply, and use I/O signals. So, what are inputs and outputs? So these are electrical signals that enable the robot controller to communicate or talk to other things, such as the robot itself, end-of-arm tooling, i.e. grippers and things, sensors, actuators, or other equipment. Again, it normally is going to be hardware and signals, and again, sometimes you can group things and do specific functions, so we'll talk about that. So again, let's talk about what things you're using I/O signals with. So the first thing we're going to talk about is sensors. And again, sensors will come in as inputs into the robot, and they're sensing something happening in the world. And these could be a limit switch, proximity sensor, photoelectric reflective or through beam, or a pressure amount. You could have something, and an air pressure, things like that. So let's talk through some of those. So limit switches, again, a couple different types here. So basically, as something comes and hits this limit switch, it makes a contact inside, which then goes into the robot input. Proximity sensors detect the proximity, usually of a piece of metal. So you have a metal tab, it comes down close to the proximity target point, either the cylindrical one or on the end of the square one. As it gets close, it makes a close contact, and the robot can read that sensor. You have photoelectric, reflective, and through beam types. So again, photoreflective or photoelectric sensor just means it's shooting a beam of light somewhere, and somewhere there's a receiver. So this one's actually shooting it out, reflecting it off of something and coming back. So this would normally say it's on or whatever, but if something blocked it, it would then change the state of that. So you have one that's reflecting. You can also have them set up as a through beam. So I have an emitter and a receiver here that are shooting out, and if something blocks that. And you can also have one that's just shooting out into space, and if something, especially a light colored object, gets close to it, it will reflect it back. So there's a lot of different ways of doing things with photoelectrics. In other ones here, again, just how it comes through. You have a reflector in here that normally is making this signal until something breaks it. Sometimes you can reflect right off the target. And again, sometimes you have an emitter and a receiver, and something comes through. And again, this is basically the way a lot of garage door openers check to see if there's somebody standing in the way of the garage door. So if you have one that's set up properly, it should have a sensor that should have a transmitter and a receiver. Again, and if you stand there, it will stop you. So if you want to see one, go check out some garage doors. Actuators or outputs, these are things that the robot's turning on. Solenoid valves, actually more mechanical solenoids, relays to drive other equipments or drives are some of the common ones. So again, these are outputs. So solenoid valves, they're usually controlling either compressed air or hydraulic, which is oil under pressure. They can be single acting, which means there's one solenoid on here, and basically it's a spring-loaded return. You say with the signal off, air is coming out of one port. With the signal off, air is coming out of one port. You put the signal on, the air shifts to the second port. You can have a double activating cylinder where, again, it may be set up such that you need one signal on and it comes out one port, or the other signal on, it comes out the other port. Things like that, again, can give you some control. And some of these are detented, so once the signal's on, it stays there and doesn't shift until you pull it back with another opposite signal. Again, so what are those solenoid valves controlling? Well, it could be things for compressed air, air cylinders, or grippers. So the grippers on our robots are controlled by small solenoid valves that are opening and shutting air valves that are then connected to the gripper. You can also have hydraulic or pressurized oil. These will tend to be larger and much more force. Again, you have to put actually a little mechanical solenoid, which will come and push out with, again, a certain amount of force. These tend to not put out large amounts of force, but can be useful. Or you can actually turn on a relay that then can power other higher energy devices, electrical energy. You're probably not going to directly turn on, say, a 5 horsepower motor with the robot output. It doesn't have enough current carrying capacity, but you could turn on a relay, which then could have enough current carrying capacity. And this is basically, this internally will, with a low current amount, low energy amount, will turn on a larger energy circuit. Other inputs may be push buttons that you have around in this system that you wire up, waiting for an operator to do something, push button, a switch, something like that. And then you have output indicators. So you have lights and horns, and we have lights and horns on our equipment. These talk to, give information to the operator. And then you can use your I/O to communicate with other equipment. It could be another robot. Maybe 2 robots are sharing a workspace and you want one robot to let the other robot, I'm out of the way, or I'm ready to accept things. Could be a programmable logic controller that's controlling things, or any other sort of controller you might have in your system. And again, these I/O signals you can turn on, you can turn off, you can set to a value. Again, if supported. Digital I/O is usually on and off. We'll talk about that. Other things, analog and group, you can set to a number. Again, inputs, you can read them. Their values stored and decisions made. When we talked about if statements, we talked about I/O, and we'll just review that a little bit later as well. And again, when you look at a signal, it defines what it is. For instance, DI1 means it's digital input 1. GO2 means it's group output 2. So usually it's pretty simple. Digital, group, analog, input, output. It's pretty easy to usually figure that out. So, for the standard ones, however, we have some unusual ones. We have user operator panel, standard operator panel, robot inputs, outputs, digital input outputs, group input outputs, and analog input outputs. So, talk about these first 2 to start out with. So, the system, controller system provides again, 18 inputs and 20 or 24 outputs that can connect to your remote device to control a robot. And these are basically operating like a control panel would be for starting and stopping the robot and things like that. So if you're having, say, an overall PLC run the whole system, it will start up the robot automatically on itself, things like that. Again, sometimes there's a process I/O board into this that the user operator panel is connected into. You can also set it up to be regular digital I/O. So if you do that, you can double assign I/O to be both user input output and digital input output. And that allows you then to do things with the user I/O using digital input output instructions. The standard operator panel, so that was user operator panel, this is standard operator panel. Again, this is what is physically on the front. You can't change those assignments. They're hardwired in, obviously, but sometimes it's useful in your program or wherever to see, did somebody press the start button, things like that. So those can be useful things to do as well. And we have robot I/Os, and again, there's a lot of signals going through controlling to the robot's motors and brakes, but there's also some other specific I/O signals you can get there. And most importantly are the ones that go out towards the end of the robot that are used for controlling the end effector, end of arm tooling. Again, these are there's a connector called the EE connector on there. You can also get them outside. Standard is 8 inputs, 8 outputs. For a total of 16 points. Again, they are generally 24-volt DC signals, and again are hardwired to connector EE on the robot itself. Now, digital I/O is one of the common ones. These are just signals sent to and from the robot controller. Again, they can either be on or they're off. It's like a light switch. It's on or it's off. If you don't have a dimmer on it, you can't turn it halfway and have it be halfway on. Again, this is one line of one physical wired in line that you get into it. You can Configure them to be controlled independently or in complementary pairs. We'll just talk about that the next slide. And you can set the polarity on that, so you can get it so normally when you make it on, it energizes the circuit, but you can inverse that so that when you make it on, when you turn the signal on, it actually shuts off the electrical signal. So this complementary pairs, so what this means is if you have 6 and 7 are set up as a complementary pair, when 6 is on, 7 is automatically turned off. So it's a way of, if you know, especially this works on double solenoid cylinders and things like that we talked about, where you don't want both solenoids on at the same time. That's its common way that it's used, but it can also be used on some messaging communication type things. So something you can do to that. It's still good practice to shut 7 off in your program, but it should go automatically. Now just going over some of the hardware on the different robots. So the R300IB Mate has 28 digital inputs and 24 digital outputs available without adding anything else. They're inside the unit. Okay. And again, rack starts with rack 48 on that case. Also 6 IOs on this 6 robot inputs and 6 robot outputs. Also, there's another optional configuration to the EE connector, and there's also the option of having them wired straight into solenoid valves. So on our robots in the classroom, the end of arm tooling is controlled by solenoid valves, which are actually wired directly into that. We can also take a group of digital inputs or digital outputs, and we can control them not individually but as a group. So this is a group of up to 16. It can be lower than that, up to 16s. Again, remember, digital outputs are either on or off, so we take those, combine them up, and this is basically counting in binary. So you ever heard people talk about that? That's what we're talking about. Again, then you can look at that by setting one instruction. You can set up to 16 IO with that. And we'll talk about that a little bit more. And analog IOs is the last one we're really going to talk about, and that is can have a range of values. So this is more like having a dimmer switch on a light. It doesn't have to be on or off. It can be partially up. So there's a lot of things. Let's say if you have a pressure reading, you want to control, you want to read what the pressure is exactly. It's not on or off necessarily. You want a range, or you want to control a pressure or something like that. Typically, they're either minus 10 to 0 volts or 0 to plus 10 volts. There are some that are minus 10 to plus 10 volts, so there's a lot of different varieties out there. Depends on your physical I/O. Now, when you read this, you actually get that number converted to a value. So maybe there's 1,000 possible points in there, and you get a number between, say, 1 and 1,000. So looking at those actual IOs, and this is an older unit, but it's a lot simpler to look at than what we have. The Model A modular IOs, and we'll talk about this as racks and things like that. Again, communicates through an interface, and again, you get digital input outputs on each of these cards. You can have the analog inputs on a card. So each of these card slots could be digital input outputs, 8, 16, or 32, or an analog input output card. The Model B has distributed I/O as an option. So this is a I/O box that can be mounted really anywhere. It doesn't even have to be in the same robot controller. It can be mounted anywhere. Communicates via serial communication line. You don't put it in the back plane, and the I/O get wired to these screw terminals. Again, this is digital only. 24 volts or 120 volt modules you get for this. You don't have a lot of option. You're picking one or the other. Then we have I/O options. Again, you have robot I/O, process I/O, that Model A modular I/O, Model B distributed I/O. You can also have networking ones through device net, control net, Profibus, and Ethernet. So these are generally what you're going to use a lot of times to talk to a PLC or an overall computer controlling things. And some of these are specific to certain hardware. Ethernet's probably the more common one going now, and it's a pretty generally used one here. And so if you look at what these would have in there, process I/O, robot I/O, Model B, and then these other ones, which are basically cards that you may add into it, or the robot controllers now come with some Ethernet in them built in. So as you assign your I/O, the first one is the rack. That's sort of, again, physically where that module or board is mounted. Again, there are some rules about that. Again, you're doing Model A or B, starts at rack 1. You then count up sequentially. If you're using one of these other network ones, for instance, Ethernet starts at rack 89, and so forth. Second is, part of the assignment is the slot number. So on a physical rack, it's which one of those slots, and we'll look at a picture that has that. That's sort of which I/O module it is onto it. Again, slots are 1 through 10. And some simple things like you can't use slot numbers twice in the same rack. And then after the rack and the channel, we have the starting point. So this is the physical location on that I/O module that identifies what the first point is. If you're an analog, and remember these are ones that have this variable, say 0 to 10 volt range, physical position of the port on the I/O process, and the terminal number are used in that. So if we look at this again, this Model A makes the most sense. So this is a rack, say rack 1. This is everything in rack 1. At the left is sort of the control part of it that controls and interfaces to the rest of it. And that's slot 0, you don't use that. And then slot 1, slot 2, slot 3, slot 4, and slot 5 at the end. So slot 1, rack 1, 2, 3, 4. And then the next one is the starting point. So we look at where the starting point is on that. You look on the card and where it's starting to. Okay. Again, this very dependent on which I/O system you're using. So in this it would be rack 1, slot 1, digital input 1 through 8 starts at position 1. Now it's a little confusing because, see it better on this one, inside this they actually call it A0, but we're going to call it position 1. So we have 8 I/Os here, not 0 through 7, 1 through 8 is how it's really defined inside the robot controller. All right, so 1 through 8. Rack 1, slot 1 starts at 1 would be up here. Okay, now let's talk a little bit about group I/O. So in this case, if I have 4 outputs that I'm grouped together, digital output 1, 2, 3, 4, and 5, and we look at a chart here, and these are binary bits. So red indicating it's on. And how we work this is if this position DO1 is on, that's worth 1. This is worth 2. This is worth 4, 8, and 16. Okay. So if I set group output 1 equal to 17, if this is my group output 1, 1 and 16 would be 17. So again, this group output, if I make group output equal to 1, this are the 2 digital outputs that will turn on. So you turn on to 17, and now it comes on. So again, what does that mean? Well, it really takes a binary integer and puts it out, and we're just going to look at the first 4 because it goes on and repeats forever. Let's just sort of zoom in a little bit to see a little bit more. So if our binary number or the integer number we give is 0, that means they're all off. That's kind of an easy one. If it equals to 1, digital input 1 is on. If it equals to 2, remember this is equal to 2, now this column digital in number 2 goes on and 1 comes off. And make it 3, it's 2 and 1. So you see it's counting up in binary. Binary kind of freaks you out a little bit. You know, you can just have a chart like this and say, what do I want to be on and off? And look at this and just say, I want this on and that on and that on. So this means I make it to be 11. You can certainly, as you get to be larger numbers, it becomes a little bit of a problem. We're not going to make you have to memorize how to do any of this. So configuring group I/O, again, has to be made up of a sequence of consecutive digital I/O numbers. Again, they're configured by the rack slot starting point number of points. Again, adjacent, no skipping between points. But again, they're going to be previously identified digital inputs or outputs. So, seems like a lot of sort of headache. So why would you want to do this? So let's say you need a PLC that needs to indicate which of 3 possible parts is currently in process. So the robot does different things depending on whether it's parts A, B, or C. So you wire 3 lines from the PLC to the robot. When part A is running, line 1 is on, part B is running, line 2 is on, and part C is running, line 3 is on. So it's pretty simple. But if, say, you have 30 inputs, 30 different parts to do, rather than wiring 30 different wires between the PLC and the robot, you could wire them 5 and use a group input. Now, how do you get that? So you use 2 to the however many inputs you have gives you possible states. Again, if you come back and look at this, you don't usually use all offs as an actual valid signal, so it's frequently that number -1. But 5 wires would give you 32, 6 would give you 64, and so forth. Now, and you've done some of this in class already with the laser. But again, you can monitor each of the different types of I/O. You go through, and we'll go through this a little bit, but in this case, digital output 1 and 9 are on. You see they're on. They're shown in green there. So setting, we're going to be very big here. Before you force, manually turn on any I/Os or even simulate any I/Os, especially when you're forcing outputs. An output is going to make something come on in some cases. So far we've been turning on a little laser. Now that's not terribly dangerous, but if it was a laser that can in fact cut through steel, it would be dangerous. So anytime you're forcing or simulating any outputs, simulating any inputs, you have to make sure you're doing it properly, understand what the effects are going to be. Okay, so you should simulate them only for testing and troubleshooting. So this is basically, let's say I don't have a certain, say, push button already wired in. I'm waiting, the electricians haven't wired up yet, but I want to run my program. So your program runs to a point it's waiting for an operator to push a button. You could then, through the teach pin, go and simulate that and say, I'm going to pretend like it's on. Same time on an output, you may not, maybe you want to run the robot and not have something actuate. So instead of actually running, you're just going to simulate its output. So you can do that. Again, and make sure that when you're done doing your troubleshooting that you unsimulate all those things. Otherwise, say if you're waiting for, say, that operator push button and you leave it simulated on, then everything gets running again, and instead of waiting for that operator button, because it's already simulated and forced on, it will just go ahead and say, yes, it's already pushed and go forward. So you need to be careful of that. So again, you've done this with the laser. You go to the I/O, you go to the inputs, and you run to the one you have the on-off. All right. If you're simulating for outputs, for inputs, to force it on and off, you have to simulate it. Okay, so inputs must be simulated, and do that. We'll go over a little bit how to do that when you go to that arrow, and it'll simulate will come up. Again, changes a bit without actually going in or out of the robot. Again, it's usually used for testing before you have hardware in place, or if you don't want the peripheral devices to actually operate. So just more to check logic. Again, but remember, once you simulate them, they're never going to go out, or you're never going to base it on real life happening. So you just have to make sure. And again, there's easy ways of unsimulating all that function, you go and you can unsimulate all I/O and get rid of that all at once. Okay, the I/O screens, and the I/O button on your teach pendant down there at the bottom, you do that, and up comes a screen kind of like this. Again, frequently you're going to press type, and up will come this, and now you can press which one you want to go to. So let's say you press digital selected, maybe inputs or outputs. You want to toggle back and forth between inputs and outputs. You just press the in-out key, it'll go back and forth. All right, and you scroll down to the number you want, or if it's way down, you can press that item key on the teach pendant and put in, say, 101 for the laser. So item 101 will take you right there. And then pressing the on and off key will turn that output on or off. And again, most of you have done that in the labs already. And then you can look at detail for that. So for this one, you can go to the detail. Give you the comment for it. Okay. Digital inputs, again, you have to simulate, big yellow simulate button. You can unsimulate, you simulate it, goes to yellow S. Again, this simulated column tells you what's simulated and not simulated. So digital inputs must be simulated before you can force their status. Again, inputs, again, you have that to configure I/O, you go to the status screen, which is this, and press the configure button here. So press the config, come in here, digital input, tell you the range for this, which rack slot it's in, and you come up over to it, just enter in the appropriate racks you have for this. Again, just make sure these match the physical location. Now this is normally you sort of do it once and then you're done. You don't have to worry about it. But rack slot starting address. So in this right hand column, the status, active means it's configured and activated. Unassigned means you haven't assigned those to any point yet, and that's fine if you're not physically on the system. And once you've made a change, these will actually change to pending. Pending means, I think it's actually PND, means that you need to have the power cycled on the controller. So once I do an I/O assignment, the robot controller only reads that on power up. So if you change it, you have to power the robot back down and then back up, and then it will go. And when you actually change this, you'll get a line up here. It will say, controller power needs to be cycled. Digital output configuration is pretty much the same. Group output, again, is a little different, but so versus this range here, you're doing one at a time. You go to the in-out, which rack slot, starting number, and how many points you have. You don't have to do, you can just have, I think, 2 you can do as a minimum, up to 16 as a max. So again, what do you do to use these robot outputs and digital outputs? So this is an example of the gripper open button. So as you press the tool and gripper open button, open close, let's run this program. So it'll say RO robot output 4 equals off, robot output 3 is on. And again, this off just tells you the current status that it is. Okay. Again, start out, this is because they were both off at the start. And then the close gripper, again, just switches. Now 4 is on and 3 is off. Now just how you get to those commands, just that instruction, come up to the I/O and you'll get various statements for that. And I/O statements, you can set digital outputs, robot outputs, group outputs. You can also set registers to this value of digital inputs, robot outputs, group inputs. You can set analog values, and you can kind of go on that. And remember too, you can use I/O in the if statement. So we're thinking back to that. So this is what we talked about for the if statements. If you're using an I/O, digital I/O, robot I/O, system I/O, user I/O, standard I/O, equal to, again, sometimes you can have inputs on this side to do something. So again, if statement can use IO in it as well. Again, if it's something that has more of a value, such as group input or output, which can have more than 0 or 1. So frequently it'll say if digital input 4 equals on. It says if it's on, do something. That's sort of the easiest sort of way you want to do it in most cases. If, again, group input outputs or analog input outputs can have a range of numbers. So here you're getting more complicated. So if the group input is equal to or less than 5 or something like that, you could use that. So again, this robot output monitoring screen for this grippers that we talked about, open, close the gripper. Again, robot detail for that. And again, you scroll down to the comment line to put in the comment you need. You go down to the polarity. Again, you notice that it goes from inverse to normal or show up onto your teach pennant screen now. And then finally complementary, which you have true or false. In this case, 1 and 2 are set as complementary signals. So as we're turning one on, the other should shut off automatically, though we want to force that. All right, so now once you're trying to think about how to use I/O in a program, so the very first step, and this will a lot of times sort of get you all through, is think about what all the inputs and outputs are in the system. And this is a really good thing to do when if you're doing a new system, or if you're modifying a system to get a list of all the IOs there. But if a new system, you have to sort of generate what are all the inputs and outputs going to be, what are they going to do, where are they coming from, where are they going to, what are the electrical characteristics, are they 12 volts, 120 volts, are they digital, are they analog? Then you start putting names onto them and follow that through. And then you get into sort of protocol and timing for how you're going to work with it. So timing diagrams, some people will write very complex timing diagrams of just when things are going to happen. Most of the time you can do a simple listing of sequence of saying, I'm going to move over the pickup point, I'm going to open my gripper, I'm going to go down to the pickup point, I'm going to close my gripper, I'm going to come back up. I'm going to wait for, say, a polishing station to say it's ready. I'm going to go put the part down, open the gripper, that sort of thing. Where it gets more complicated is when you're trying to communicate with something else like a PLC, and you're trying to make sure you don't miss any signals coming back from it. So frequently when like a PLC sends a signal, you may send an acknowledgement signal back. Yes, I have that. I understand that. That's what I'm going to do now. So that's where timings and writing up these diagrams can be much more complicated. All right, so again, if there's questions on this, we'll have our Thursday question and answer periods if you want to come to that. And next week we'll work on to macro commands. And thank you.